What's up? It's your girl, Jazz the Physicist, back with another excruciating prelim problem. The other one, okay, look. So we're on number 3, right? And like, show that there exists no simple group of order 56. You assume that there does, which means you can't have normal subgroups, which means there cannot be unique CeLO 7 or CeLO 2 subgroups, and then you derive a contradiction by showing that there is a unique CeLO 2 subgroup just by pigeonhole principle on the divisibility conditions for the subgroups. That's it. That's like the summary, okay? But I was still just like, it gave me a headache even writing it out. So, okay. So that's that one. I'm going to look at another problem. Hold on. I'm sorry if there's noise. I adjusted the mic volume and stuff so it shouldn't clip. I know the first video it clipped a little bit, and my bad. It shouldn't clip now though. Okay. God, this test. Anyway. I wonder if I should read the books that they recommend. No. If you are retaking a prelim, or you've already been through a year of algebra, reading the books isn't really necessary, especially now with AI. You can, if you need to refer to a definition, just go to the AI, ask it to recall the definition, and give you an example immediately. Don't go to the books. All of the books are now obsolete. And the AI can parse the books anyway. So what you can also do is you can submit the PDF to the AI, have it parse the definition for you, and then generate an example based on the framework that the book uses. So again, you don't have to waste your time on Google or Math Stack Exchange. And I guess people still use Math Stack Exchange, but the AI will parse that too. So don't waste your time searching things. It's literally like, every minute you spend trying to parse through something on Google, the AI would have spent 10 seconds and found it for you, and probably something better and more illuminating. And I'm so for real on that, so just keep that in mind. Let T denote the set of all 5 by 5 matrices with eigenvalues 4 squared and 17 squared. Sorry, I meant 4, 4, 17, 17, 17. Okay. We already know what this is going to be. Define a relation on T by these matrices are equivalent if M1 and M2 are similar. The problem's not finished, but recall similar. You know what? And you know what? Hold on. Similar means conjugate. And why don't they just call them conjugate matrices? We're talking about group theory. You go through all of that group theory, you start working with modules, and they don't use the word conjugate, they use the word similarity, but then give you a conjugacy equation. Which means there's probably a class equation or something equivalent to that in the category of modules, of R modules, of unital R modules, but who knows? Okay. How many equivalence classes does T have? Assume all matrices over C. It says justify your answer. Do you mean prove it? Okay. I mean, my justification is that I just memorized every theorem about R modules and I can just recall it from the top of my head. To me, so okay, this looks like to to get the conjugacy classes, they have to be invariant under an orbit action. Not invariant, but they have to be in the same orbit under a conjugation action. That determines a conjugacy class. So, I mean, that's not what they're going to say. I think they're just going to use Jordan canonical form. But if we're looking at this, right, and this is like a partition of a Jordan block, and this is a partition of a Jordan block, like how many ways can you do that? I don't know. So anyway, so because we are over C an algebraically closed field. Oh, you know what I just realized too? We may use the Jordan canonical form. Here, every matrix has unique jazz. Every matrix has a unique Jordan canonical form. So then, if every matrix has a unique Jordan canonical form, then this equivalence relation is at least going to be well defined. Okay, and I guess we don't have to prove that, but that is what this is going to give us. If every matrix didn't have a unique Jordan canonical form, the equivalence classes wouldn't make sense, because then things would be equivalent that you can't really separate them. Like there'd be no, essentially it'd be like a metric space failure issue. But okay, two canonical forms. Hold on. Two canonical forms are in the same equivalence. I'm writing as fast as I can, okay? Class of T if, and only if, okay. T if and only if they are equal. Wait, two canonical forms are in the same equivalence class of T. Oh, okay, yeah, two canonical forms are in the same equivalence class if and only if they're equal. Maybe up to rearrangement, like up to isomorph. I don't. Okay, look. This is how quick this problem is. I told you I'm gonna get faster. Since the eigenvalues of the matrix T are 4 multiplicity 2 and 17, I put a 14, 17 multiplicity 2, literally, why am I writing it out? Multiplicity 3, oh my god. Multiplicity 3, the Jordan canonical form. Must look like, I already said that, the blocks. 4, let me put it closer. 4, 17, 0, zeros everywhere, 0, and then A for the repeated, and then B, and then C for the repeated on the off diagonal, okay, and then zeros everywhere. I don't want to confuse, that's really just like not really standard. Maybe if I put, like, make it, that A looks like a 9. Okay. Like, make it like, if you do your own notation, it just like throws people off. So. Okay. Where A, B, and C, 0, 1. And B equals 0. If C equals 0. Therefore, there are 6 equivalence classes. It's, basically, it's when the algebraic multiplicity and the geometric multiplicity. So, like, if A is equal to 0, then 4 and 4 are distinct. If A equals 1, then 4 and 4 are in a Jordan block of 2 by 2. And the same thing for B and C. I say distinct. They're obviously not distinct. They're repeated, but it's talking about the dimension of the eigenspace. If A is 0, then 4 is in a one-dimensional eigenspace, and the other 4 is in a one-dimensional eigenspace. If A is 1, then 4 and 4 are in a two-dimensional eigenspace. So it's really showing like independence of the eigenvalues when you look at the values of B and C. I mean, of A or B and C. So if B is 0, right? If B is 0, it's the same thing with the 17. And if B is 1, then the 17s block up the way the 4s do. And if C is 1 and B is 1, then you get a block as well. So you're basically doing like, A can be 0, 1. And so, okay, let's count 6 equivalence classes. This might not be enough. I think if I just wrote this answer, they're gonna be like, how did you get that? Like, so, okay, so we can have, what else? B equals, oops, I feel like there's still, I mean, up to moving around. Did I get them all? Why am I only getting 4? Hold on. A equals 1, that's one block, but you can have A equals 0. I'm just wondering if B can be 1 and C can be 0. If that's true, we just, okay, look, A equals 0, C equals 0, and then A equals 1, B equals 1, C equals 0. That's just going off of like, I mean, if that's the case, something's wrong. Hold on. And I thought I was going to get this done quickly. Every time I think I'm going to do it quick. Okay, 14 minutes. I mean, you had to write the problem, so. me see. We're asking ChatGPT. We call it lambda here, okay? Eventually, we're gonna have to do 2 problems a video, which is, we're just getting warmed up, I guess. Yes, something subtle is off in your enumeration of Jordan forms. That's what ChatGPT says. And I've done this. Okay. Hold on. Because it should just be all, I thought all integer partitions of these numbers. For eigenvalue 4, 2 possibility. 2 1 by 1 blocks, the diagonalizable part, or 1 2 by 2 block. Okay, we already got that. That's what the A is saying. If A equals 0, then you get 2 1 by 1 blocks. If A is 1, you get 1 2 by 2 block. And that's going to determine, so, okay. So, and then for eigenvalue 17, you have 3 1 by 1 blocks, 1 2 by 2 block, and 1 1 by 1 block, or 1 3 by 3 block, okay? It says the constraint you wrote B equals 0 if C equals 0 isn't quite right. The correct relationship is... That's what the solution says on the fucking thing for the school. I'm reading off of the school solutions manual. I didn't come up with that B equals 0, C equals 0. That's why I looked at it. I was like, what? I don't even think that's why I was starting to get confused. Because when I wrote the school's conditions... So when I wrote the school's solutions on these first 4, I was like, that doesn't give me enough. So how is it that this is, like, where did this constraint come from? And now we're saying it's not even right. Okay. So yes, B equals 1 and C equals 0 is perfectly allowed. It corresponds to the mixed block. Exactly. And so if we do it the way that I wrote it out here, these are the 6 equivalence classes. And this is a freaking typo, and also not my solution because I didn't say that. This is the truth. Thank you.